Welcome to the lectures on fundamental of MIMO wireless communications. We have in the last lecture looked at white sense stationarity, uncorrelated scattering and homogeneous channels. With this we carry forward and discuss the single input multiple output channel, the multiple input single output channel, multiple input multiple output channel, and also the narrowband antenna array assumption. So we are going to discuss this, but very shortly I would like to explain one particular characteristics of the channels that what we are looking at. So I'd like to just describe the propagation characteristics which we have been discussing over the last few lectures. It's very important. So if we have a transmitter at this point and we have a receiver at this point, we have been saying that let there be an ellipse and all paths that come from this ellipse are having the same delay, which gives rise to flat fading. This is what we have described. And if there is an ellipse, so I'll draw another arbitrary ellipse, that means representing all scatterers which are in this particular ellipse. We would have paths coming like this, which are having the delay of, let's say, tau 2. Let's take a very simple example, right? So we have these conditions, and when we are trying to draw the impulse response that is received, let's say we have launched an impulse at the transmitter. So because of these, that means let's change the color, because of these ones, what do we get is after a certain duration in time, that is the delay corresponding to tau 1, we are getting echoes which are very close to each other. So this is the result of the first circle. And if we look at the delays of tau 2, that means if we proceed further and this total delay is tau 2, so we are going to get echoes which are all almost on top of each other at delay tau 2. Now if we concentrate on either of these two, let's take this particular set, what we are going to have is there are n number of such multipaths coming in, and they are coming from different directions. One could be from this direction, this direction, this direction, and this direction, which would define the angular spread. And similarly for this one also, they are coming from different directions, that would define the angular spread for each of these delays. So that means if we are able to expand the view here in the theta dimension, that means we could say that there are rays which are coming in this direction, in this direction, this direction, this direction, and hence we are, in other words, trying to describe h, that means the channel coefficient, as a function of delay. That means we already have tau 1 and tau 2, and also theta, that means the angle at tau 1 in this angle, in this angle, in this angle, in this angle, at tau 2 again this angle, and of course that's a function of time, right? So this axis is the time axis, so that gives us the delay axis, the time axis, and the theta. So this is what is actually happening in the system, is what we should visualize and keep in our mind when we are referring to the channel conditions. And although these things are going on, of course there are many more details also. This is one kind of abstraction. We would always use even further abstractions, without which certain results which are very fundamental and which are quite insightful are not possible. So please be careful at every point of time when we are moving ahead and making assumptions with using these kind of channels. And also I'd like to summarize that we'll be using a slow fading, we'll be using a flat fading unless otherwise specified. These are the two conditions that we will be using, and we will also be considering uncorrelated channels This will of course describe, most of the time we'll consider uncorrelated, so in the space dimension. So when we are in the space dimension, and we are going to also take care of correlated, right. So just quickly before we go ahead, here in this particular picture we said slow and fast, flat and frequency selective. In the space axis we have the rich and poor scattering. So clearly rich scattering scenario is one where signals arrive from all directions, and poor scattering is one where signals arrive over a narrow angle. Here signals arrive from all directions, right. So if we go by the discussion in the previous lecture, we said a rich scattering results in smaller coherence distance, a poor scattering results in larger coherence distance, right. So that means rich scattering environment would mean there is lot of reflections. So that in the spatial dimension there is lot of reflectors around, whereas a poor scattering means the rays are coming only from a particular directions and there is not too many reflections around. So poor scattering is the situation where the coherence distance is larger, rich scattering is the situation where coherence distance is smaller. So if we take two antennas lambda by 2, we can assume that the signals are uncorrelated. So that's how would we define a rich scattering environment and a poor scattering environment, and that would bring us to a kind of description in the time, frequency and space dimension of the wireless channel with which we started quite some time back. So now we move forward and try to look at the CMO channel. The CMO channel, as the name says, it is single input, multiple output. Single input, multiple output. That means we are looking at a situation where the transmitter has only one antenna and the receiver has multiple antennas. So this is the receiver. So we are trying to characterize or write down how would the channel be, or how would we write down the channel under in this particular case. This is a typical situation which we are going to encounter in the studies, so it's important that we take a look at this. And the number of antennas here we would write as 1, 2 up to M, R suffix indicating receiver number of antennas, and let us have H I of tau comma t. So if we suppress the I, it is H of tau comma t. That means the delay and time is the impulse response of the channel. So that is the impulse response of the channel between the transmitter antenna and the ith receiver antenna. So we'll use this Tx for transmitter, Rx for receiver. So this is how it is given by, and we can represent H tau comma t. So of course I is equal to 1 to up to Mr. We would write it as H1, that means the first link, H1 tau comma t, H2 tau comma t, and so on up to Mr tau comma t. H1 tau comma t, H2 tau comma t, dot 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 up to Mr tau comma t with a transpose. So transpose of this vector. So at the outset, let me remind you that we would use linear algebra, and most of the studies on MIMO communications are using results from linear algebra. So one would require the basics of linear algebra, vector operations and matrix operations to be revised at all points of time. So when we say this, what we mean is that effectively we are talking about a column. So that means H1 tau t, h2 tau t and so on up to h mr tau t. Although we are writing it in this way as tau comma t, most of the time we will be interested in talking about h of t, because we will assume flat fading. Flat fading would mean that all the multipaths are at the same point. That means in this particular picture, the red color is not present. That means only the black is present. So we don't have the red ones. So that means, or to make it faster, we don't have this red one. So only tau 1 is present. So that means all the delays, these are not present. Only the black paths are present. So if you could imagine that is the flat fading. That's just for the reminder case, just for the reminder. So only the black lines are present. So only these reflectors, no other paths. So all the delays are the same, almost the same, no red paths, only these paths. So that is when we have this. So usually we would write h of t is equal to h1 of t, h2 of t up to h mr of t. This is mostly what you would encounter transpose for the single input multiple output channel. And the received signal, so what we are going to get here is y1, y2, y3. This is what we are going to receive. So we could write that yi at the ith receiver as a function of time is equal to, ideally speaking, hi tau comma t convolved with s of t for I equals to 1 to up to mr. But what we have written over here, you could write it as, for flat fading scenario, hi, since it is no delay, it's a multiplication s of t for I equals to 1 to up to mr. So this is what we are going to get, and for I equals 1 to mr, you could write it in vectorial form. Y of t is equal to y1 of t, y2 of t up to y mr of t transpose, or we could write y of t is equal to h vector times s. So that is what is in short form. You could write s of t, h of t. We could write this in the vectorial notation as the received signal. So this clearly tells that I am receiving y1, y2 up to ymr. So mr different copies of the same signal. Whatever is transmitted over here, that means if s of t is transmitted, it's going to go through the channel, receive over here, go through this channel, receive over here, go through the channel, receive over here. So there are multiple copies of the same signal which is received at different antennas. So this is the typical single input multiple output channel. Next we move on to the multiple input single output. So that means the reverse of this condition. If we take this condition and from this becomes the transmitter, this becomes the receiver. So that is the case. So as if there is one transmit antenna and multiple transmit antennas, and there is only one receive antenna. So this is the reverse condition. Now one example of this could be, if this is the base station is pretty large, it can hold multiple antennas. This is the mobile which has only one antenna. So this is the uplink direction, and here this is the downlink direction. That means this is the base station with multiple antennas, this is a receiver with a single antenna. So this could be a potential situation that we could take it as an example. So here we would mark them as the first antenna, the second antenna up to MT, indicating the transmitter antenna. And so here there are MT number of CISO links, each of them are CISO. CISO means single input, single output. So these are the different CISO links, and here would identify each channel as HJ of tau comma t, which would be the channel impulse response between the jth transmit antenna and the receive antenna. So that is the way to write it, h of j tau comma t, and what we would have h of tau comma t, the vector is h1 tau comma t, h2 tau comma t up to hmt tau comma t, no transpose anymore. So this is basically a row vector, whereas for this case it was a column vector. There is a transpose here. That's the difference. And again, if we consider flat fading, which we'll mostly do, so in our case we can write it as h1 of t, h2 of t up to hmt of t. So this is the standard way of writing it. And now there is a slight difference between the transmitted signal and the transmitted signal. In this case, we will have S1 of t transmitted from the first antenna, S2 of t transmitted from the third antenna, S3 of t transmitted from the SMT of t transmitted from the mth antenna. So what we are going to get is Sj of t getting convolved with Hj of tau comma t by the jth link, any particular link. This is the Hj, and then at the receiver, this signal that is getting transmitted from the first antenna is getting added to the signal which comes through this path, is getting added to the signal that comes through this path, is getting added to the signal that comes to that path. So we have a summation of j equals to 1 to mt, right? And of course there is some noise. Okay, so this is the received signal y of t. So if you look at the fundamental difference between the h of t there and the y of t here and the y of t there, the difference is here y of t consists of several y's. That means I have received 1, 2 up to mr number of copies. Here I have received only one y, but I have transmitted mt number of copies. So that's pretty natural, and it goes by the name. And here each of this link would have a noise associated with that, whereas here there is only a single noise added to the combined component, simply because there is only one receive antenna. So with this, if we move ahead, and the next natural step for us would be to describe the MIMO case. So that's the first time we are encountering MIMO, multiple input, multiple output. So in this case, naturally it's a combination of the previous two cases. So what we have is the H matrix. Now we write it in capital H. This is usually the notation. So the way we have come across is we have started from time, frequency, now to space, and then we have taken Fourier transform of the channel in the delay axis, in the time axis, inverse Fourier transform from the Doppler axis, then there was the space, this angle. There are so many things that are going on. You would often get confused with the number of variables that are required. So in many cases, when you are not studying the space dimension, that means when you are not studying the multiple antenna dimension, usually people usually the habit or the technique is to represent capital H as the Fourier transform of small h, and that means we are talking about the transfer function of the channel. But when it is the spatial dimension, the usual notation is to use the capital H, but there are many places where people would use a C, they would use a G, or they would use a small h. So we would go by this because we are taking a flat fading channel, so that's not going to confuse us. So this is the notation that we're going to follow. But as of now, what I write here is not with flat fading, this with full fading statistics. So that means H11, right? So here we describe that transmitter has MT number of antennas, transmitter has MT number of antennas. Similarly, the receiver would also have MR number of antennas. So this link would be H11. This is received on antenna 1, transmitted by antenna 1. The second antenna link, if I draw the second antenna, that's for sake of convenience. So this link, if you look at it, goes to the second antenna 1, 2, H of received in antenna number 2, transmitted from antenna number 1. Similarly, this particular one is H received in antenna number MR, this is MR, transmitted from antenna number 1. Whereas this link is denoted as H, which is received in antenna number 1, transmitted from antenna number 2, and this link is H received in antenna number MR, transmitted from antenna number MT. So this is how the typical link description would happen. So here H11 means this particular link, it is tau comma t, I can simply write HT, and then H1 comma 2, which would mean received in antenna 1, transmitted from antenna 2 of t, and so on up to received in antenna number 1, transmitted from antenna number MT, function of time. Just a quick reminder at this point, these we have taken them flat fading, so they fluctuate in time. There is a time axis, they would fluctuate, right? And if you take the Fourier transform of this, you are going to get the Doppler spectrum, or sorry, if you are going to take the autocorrelation and take the Fourier transform of that, you are going to get the Doppler spectrum. Whatever you have studied would apply for these cases. So here we have H of 2 comma 1, that means received in antenna 2, transmitted from antenna 1, and dot 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 up to H MR comma 1 of t, this would be H22, and so on. Here we are going to get HMR MT as a function of time. So this is how the full model would be. So I'd like to go back a little bit when I say the multiple input single output. In this case, so the vectorial notation, we could write it as y of t is equal to h of t times s of t, where s of t is given by s1 of t, s2 of t up to smt of t and a transpose. So that would help us in describing the equations. So this is the vectorial equation, and that means we have this row vector, we have the column vector, so we have a single scalar as the output in this case. Now we move ahead here. So s of t, since we have multiple antennas, s of t would be defined as in this case where we have multiple input, s of t is defined in this way. So we for every channel the link, the output is this one, every receiver antenna the output is this one, and there will be MR number of receiver antennas. So that way the expansion has to happen. So we could write that Sj of t is the transmitted signal from the jth transmit antenna, and yi of t is the signal received in the ith receive antenna, I equals to 1 2 up to MR, j equals to 1 2 up to MT. So y of I is equal to sum over Hj of t times Sj of t, right? Of course, Hij sum of j equals to 1 to MT is the received signal. If you would represent in terms of tau, then of course there a convolution sign has to happen. That means if you say Hij tau comma t, then there is a convolved with Sj of t. And in vectorial notation, this could be written as y of t vector, because 1 yi equals to 1 2 up to MR is equal to H. I put a double underline to indicate it's a matrix. I put a single underline to indicate it's a vector. The y is a vector because y1, y2 up to mr is equal to H times S of t. So this is a function of time, this is a function of time. So if you look at the matrix notation, it is a matrix, this is a vector, and this is a vector. The size of this is mr cross 1, the size of this is mr cross mt, size of this is mt cross 1, and of course there is noise, and noise is naturally mr cross 1 because there are mr number of received links. So that means this one is y1, y2, y3 up to mr, and each received link, each signal that is received here is a combination of the transmitted signal from all the transmit antennas. The mrth received signal is also a combination of the signal that is received from all the transmit antennas. So with this way you could represent the received signal when transmitted from multiple input multiple output system, and this combination, this particular final expression that we are writing over here is giving us the expression to take care of all situations of whether we have a CMO case, a MISO case, or a MIMO case. In case of CMO, if you are having a CMO case, in this case single input multiple output, that means MT is equal to 1, MR is equal to of course MR. In case of MISO system, you have MT equals to MT and MR equals to 1. In case of MIMO system, you have MT equals to naturally MT and MR equals to MR. So that means you have this this particular matrix at hand, which is useful, whereas in other cases just these numbers would help with this. So if we take one particular example, let's say CMO, MT equals to 1, that means this is only 1 that is transmitted, whereas MR equals to MR. So we get all these values. If we take a MISO system, that means MT equals to MT, that means this is a row vector, this is a column vector, so this gets multiplied, becomes 1, MR equals to 1, so this is 1 cross 1, so we have a scalar. So this particular expression or this particular structure takes care of all the three combinations that we have, and our study of the MIMO communication system would be based on this particular model that we have just written down. Thank you.